Good evening. Myself Chandu Putangale. Again, today we are going to continue the topic of IR spectroscopy. Yesterday we did some mistakes while recording the video. Today we are not going to make any mistake. We'll try to further improve the things better way, and I will try to explain you better way. Let's recapitulate the things what we have learned yesterday. We started the IR spectroscopy. What is the IR spectroscopy? We have seen the basic principle of IR spectroscopy is that the molecule must have the change in dipole moment. Molecule must have the change in dipole moment. So what is the dipole moment? Mu bar is equal to R into Q. Q is what? It is the charge, and R is the separation between the two charges. It is the Q is the charge. So therefore dipole moment is the product of separation of the charges. Then we have seen the different regions, different way of expressing the regions of the IR spectrum, like region in the nanometer range, 700 nanometer to 1 nanometer, 4000 to 4000 centimeter inverse to 400 centimeter inverse. Like that, we have seen the different region, different way of expressing the IR region. Then we have seen the what is the energy level diagram of simple diatomic molecule. If you take the HCl molecule, and suppose this one is the hydrogen and this one is the chlorine, hydrogen chlorine, and this bond is going to expand and this bond is going to compress. This is position of the hydrogen. This bond is going to expand and compress, expand and compress. This is the compression side, this is the expansion side, and we are getting this like this, and this distance from this distance is equilibrium distance. Therefore we can take it as the R equilibrium distance, and this distance going to change. This is the position of the chlorine, this is the position of chlorine, and this is the position of the hydrogen. It is going to change. We have seen that like heavier one is the heavier atom and another is the lighter atom. In that case, that is called as the decoupled vibration. Only one atom is going to vibrate and another atom is supposed to be stable. It is not actual case. In real case, it is not stable, but it is supposed to be stable. Therefore the bond is vibrating, and this distance, if you try to put the diagram, then we will get the different energy level. And this is the changing in distance of the hydrogen with respect to chlorine, and we are getting the different bond length, and therefore we are getting the different energy levels. Now we know that from quantum mechanics, all the energy levels are quantile. All energy levels are quantile. Then we have seen the coupled and decoupled vibrations. Coupled and decoupled vibrations. Now, how the coupled and decoupled? If the two atoms are vibrating simultaneously, then that is called as the coupled vibration. And if one atom is vibrating, one atom is going one side and another atom is going other side, that is called as the decoupled vibration. Now, we were up to Hooke's law. We have seen the Hooke's law, that is force is directly proportional to the displacement, or F is equal to minus kx with constant value. Now, what we are going to study today? We are going to study today is calculation of the energy level. Calculation of the energy levels. What calculation of energy levels? Which kind of energy levels? The molecule which those are having the vibrational energy level. This molecule is vibrating, means it is having the energy level. It is having the energy in the region. In which region? In the IR region. The vibrational frequency matches with the IR frequency. This is the IR radiation and vibrational frequency. This wave is having the frequency. Frequency is what? Frequency is expressed in the hertz. It is the number of cycle per second. Number of cycle per second. Number of cycle per second. Number of cycles per second. Number of vibration per second. Number of cycle per passing. This cycle, wavelength cycle passing through a point, that is again frequency. This vibration also, it is the frequency. Now, the vibrational frequency is given by, from where it is given by? It is given by from the quantum mechanical calculation. Quantum chemistry or quantum calculation. We are not going to derive the any equation here. We are going to write directly the equation. For derivation, you can learn the quantum chemistry. In quantum chemistry, all the derivations are there. Therefore, we are not going to derive the equations here. Now, this HCl bond or any kind of molecule bond, this is having the vibration. Therefore, this is having the oscillational frequency. Oscillational frequency. Before calculating, we will learn one thing, that is harmonic oscillator and anharmonic oscillator. Anharmonic oscillator. Remember that? Oh, I have written A here. Anharmonic oscillator, not U. Anharmonic oscillator. Harmonic and anharmonic oscillator. We will try to learn within a minute what is the harmonic and anharmonic oscillation. So, suppose this bond is vibrating. Suppose if I try to stretch this bond, this hydrogen and this chlorine bond, it will be straight, and again it will go to the original position, or it will go to the some little bit distance. It is like the spring. If you try to pull the spring, again what will be the position? First position of the spring will be like this. Again next time the spring will be at the equilibrium position. Again it is vibrating. Therefore, the periodic vibrations are called as the harmonic oscillation or periodic oscillation or harmonic oscillation. Then, if you try to pull this spring more and more, the point will come, the spring will break out. Like that, if you try to pull this bond more and more, the bond will be break out, and it will not go to the original position. That is called as the anharmonic oscillation or anharmonic oscillator. Now, this oscillational frequency, this is vibrational frequency, that is called as the oscillation frequency, that is given by omega oscillational. It is written as the omega oscillation. Since it is the oscillational frequency, therefore it is written as the omega oscillation, that is given by 1 upon 2 pi under root k upon mu. What is k in this equation? Oscillation, omega oscillation is the oscillation frequency. 1 upon 2 pi is the constant, k is the force constant. We have derived this force constant in the rotational spectroscopy. We know the value of this force constant. K is equal to 4 pi square c square mu, like that. We have calculated already there in the rotational spectroscopy. What is this mu? Mu is the reduced mass of the system, that is already we have learned again in the rotational spectroscopy, that is m1 m2 divided by m1 plus m2. That is the reduced mass of this system. Which system? This HCl molecule system. HCl molecule system, reduced mass. Now we know that how to calculate the reduced mass of the system. This is the vibrational frequency, that is in the joules. Joules. The frequency is in the joules. Remember that while writing the joules, we have to write like joules. If you are writing in the full form, we have to write like this, starting with the small j. If you are writing in the short form, we have to write only j. Capital J is written, this is right. And if you are going to write joules, the way of writing is wrong. This is the right way, this is the right way. Remember that while writing full form of joules, we have to write small j. Remember that. Now, this oscillation frequency is expressed in the joules. Now next thing is you remember this one. Now next thing is we try to calculate the energy level. That is again this calculation of the energy level will be directly in rotational spectroscopy. We have calculated the energy level is equal to s square upon 8 pi square IBC into j plus 1, like that. J into j plus 1, that is in the joules, that we have already calculated in the rotational spectroscopy, where j is called as the rotational quantum number. Like that, we are going to calculate this vibrational energy level, that is given by E is equal to V plus 1/2 H into omega. H into omega oscillation. H into omega oscillation, that is in the joules. Where omega oscillation, we know already what is the omega value of omega oscillation, 1 upon 2 pi k under root k upon mu. Now this V is not the V, this is what? This is the vibrational quantum number. Vibrational quantum number. And this equation, that is, we have derived from directly from the quantum chemistry calculation. There is no derivation. If you want to more detail about this derivation, we can go to the quantum chemistry. We are learning here in the spectroscopy. Therefore, we are not dealing with this derivation of this equation. Now, this joules, this energy can be expressed in the centimeter inverse. That is in the wave number. Centimeter inverse, that is in the wave number. That can be given as epsilon is equal to V plus 1/2 H into omega oscillation divided by Hc, that is in the centimeter inverse. This H will get cancelled. Therefore, epsilon is equal to V plus 1/2 omega bar oscillation centimeter inverse. Omega bar oscillation centimeter inverse. This energy we have expressed in the centimeter inverse. How it is done? This original equation to this equation, we know that. What do we know? That E is equal to H nu. We have learned this equation. One equation is this one. Another equation is this one. Another equation that we have learned is omega oscillation is equal to 1 upon 2 pi into under root k upon mu, that is in the joules. If you want to convert this into the centimeter inverse, how we can write? Omega bar oscillation is equal to 1 upon 2 pi under 2 pi into c under root k upon mu, that is in the centimeter inverse. That is in the centimeter inverse divided by c. That is how it comes. I will try to explain. E is equal to h nu. We know that. E is equal to h nu. We know that. Nu is equal to what? Nu is equal to c upon lambda. Therefore, this E comes out to be E is equal to h c upon lambda. H c upon lambda. Now, h c upon lambda. Now, this is what? Nu is frequency. Frequency of what? Frequency of electromagnetic radiation, EMR, electromagnetic radiation frequency. Now, this omega is what? Omega oscillation is what? Frequency of vibration. Now, instead of writing E is equal to h nu, we can write E is equal to h omega. Omega is what? Frequency of oscillation. And this h omega. Now, E is equal to h omega is what? C upon lambda. Therefore, if you try to take inverse of this 1 upon lambda, then for that is this equation will be rearranged E divided by Hc. This 1 upon lambda. If lambda is expressed in the centimeter, this will be equal to centimeter inverse. Therefore, E divided by Hc. Therefore, we have divided epsilon divided by epsilon is equal to E divided by Hc. Therefore, this is the value of E. If you divide simply by Hc, this H will get cancelled. This comes out to be this, and this omega oscillation is nothing but the omega bar oscillation is nothing but the omega oscillation divided by c. Now this quantity is in the centimeter inverse. This is the energy level, vibrational energy level present in the IR molecule. Since it is the nearly about 14 to 15 minutes, we will try to explain in the further things in the next video. Don't forget to comment below the video, please, so that I can do the things better. If you are understanding or not, please do comment in the link below. Therefore, what we have learned, recapitulate the things. We have learned all these things yesterday. We have learned how to calculate the energy levels of the vibrational energy level. Thank you. I will put next video by tomorrow. Thank you. Bye.